Hello and welcome. In this video, we're going to take a look at the basics of n-dimensional space. Now, n dimensions here, that means we can talk about as many dimensions as we like. Let's start off with easy cases like 1 and 2 dimensions that should already be familiar. We'll take a look at 3 dimensions next, which is something that we can visualize, although some of the concepts may not be totally familiar in terms of mathematics and calculus. And then we can venture beyond that and really see that as we add another dimension on, a lot of the concepts that we're already taking for granted kind of remain very, very similar. So let's start off with the basics here. Let's start off with 1 dimension first. In 1 dimension, we simply just have our real number line. We could label this real number line, let's say, as x. Real numbers, that includes all of our natural numbers, our integers, our rational numbers, and our irrational numbers. And really, we only need the one axis. We denote the real numbers with r with this double bar. And if we wish to have a point on this number line, we might just say x is equal to a. And we could denote that here as just being some sort of marker along that axis, or a point. We shaded it in a solid dot, labeling the point where x equals a. Okay, that's 1 dimension. Now let's expand that to 2 dimensions. As we add another dimension, we're going to need to also have a brand new axis. So in 2 dimensions, we may have a second axis here. We can label that as the y-axis. And now this is a real number line with another real number line that is perpendicular to that. We've got our real number line from the x-axis and a real number line from the y-axis. And if we were to look at a point in 2-dimensional space, then we would have to have an ordered pair, a comma b. Now, an ordered pair isn't an element of R. It's actually an element of the set R cross R. And we'll be taking a look at that cross product and what that means a lot more in future videos when it comes to vectors. But we denote this as R squared for convenience, or just R2. So with a single dimension, we have x equal a. And in our set R2, then we have x comma y equal to a comma b. What if we were to add a 3rd dimension now? Well, the moment we try to add a 3rd dimension, we need to add another axis, and it has to be perpendicular or orthogonal to both of our current axes. Now, the only way we're going to be able to do that really accurately is by having this extra axis go either into the page or out of the page. But since we're trying to draw this on a page, then we have to be a little bit clever with perspective. So what we'll be doing is we'll be taking this y-axis and we'll be maybe putting this at a slight angle to give a sense of 3 dimensions. Here's that y-axis. Now we have to imagine that there's some kind of perspective here and that this still forms a right angle. And instead of having our extra axis come out of the page, this time we can make it look perpendicular to x and y with this perspective. And so we'll create the z-axis, and we have to assume that it is perpendicular to the x-axis, which it does look like it is here, but we also have to say it's perpendicular to the y-axis, which is really only implied by this perspective. Now that we have 3 axes, we have 3 separate real number lines, and that forms R3. And R3, or R cubed, is just this shorthand notation for R cross R cross R, and that consists of ordered triples. So a point here in our 3-dimensional space has 3 coordinates, and we might say that this particular point is a comma b comma c. Now it's important to note here that the directions of positive x, positive y, and positive z are not arbitrary. You've gotten used to drawing x and y so that you have usually x pointing to the right of the page and y pointing to the top of the page. That's okay, that's going to stay exactly the same. You can see that that hasn't changed even in this perspective. But we have to use a particular rule in order to make sure that z points in the correct direction. You can use the right-hand rule by putting your thumb in the direction of the x-axis and your fingers in the direction of the positive y-axis, then your palm should point upward into the direction of the positive z-axis. And that's called the right-hand rule. We'll be using that a lot later as well. Now remember that when we have a point in R2, A, B, that means that we need to count in the x direction until we reach A, whether a is positive or negative, and then count along the y-axis until we reach b, positive or negative, and that will give us the location of our point. Well, very similar, the coordinate ABC in R3 is also given in terms of its x and y and z components in that particular order. So this would imply that this point ABC is at the location where x is equal to a, y is equal to b, and we can already find where that would give us as a point, and c is then along the z-axis. And that would travel us either above or below what we call the xy plane and put us into this third dimension now. Of course, mathematics doesn't just stop when we have 3 dimensions. We can continue this on and think about what R4 might look like. Now, to get a bit of an understanding of R4, or 4 dimensions, is we need to take our x, y, and z axes and add one more, but it needs to be perpendicular or orthogonal to all 3 of our existing axes. Now, stop and think about that for a moment. Would that even be possible? Well, the answer is yes, it is possible. But unfortunately, we are existing in 3-dimensional space and we can't quite visualize that 4th dimension. So at this point in time, it doesn't help to try to imagine it as a set of axes, but it is still useful to think about every point in R4 as being an ordered quadruple. Just like with all of the lower dimensions, R4 is simply just R cross R cross R cross R 4 times. But that extra axis is going to be impossible for us to try to visualize. So let's just put this all in general terms. Rn is R cross R, n times in total. And instead of having ordered pairs or ordered triples or ordered quadruples, we call this an n-tuple. An n-tuple is an ordered list of the coordinates in each of these dimensions. So rather than x equal a, y equal b, z equals c, and so on, depending on how many dimensions we have, it doesn't make a lot of sense to always have a new letter. Oftentimes we just number these different dimensions. So we would have a1, a2, a3, and so on. And our last value in this n-tuple would be an. That would be our coordinates for a point in Rn. And in general, if we are labeling the axes instead of labeling the axes x, y, and z, if we start getting too many dimensions, then we typically just label these axes x1, x2, x3, and number them until we get to our nth dimension. Makes a lot more sense than trying to come up with a brand new letter in the alphabet every time we have a new axis. We've got plenty of numbers. We have all of the natural numbers that we could possibly need. So we'll just number them if we get beyond 3 of these axes. Now let's take a moment and just dive in a little bit on how we might visualize R3 on a 2-dimensional piece of paper or tablet like I have here. Now in 3 dimensions, it's very common to visualize the axes and coordinates by using what's called first octant view. Now if you go back 1 dimension to 2 dimensions, we have 4 quadrants, and those quadrants will happen when we have x and y positive. That's our first quadrant. Our second quadrant is where x is negative and y is positive. Third quadrant, both x and y are negative. And our fourth quadrant, x is positive and y is negative. So if you think about it, x and y have 2 possibilities, positive and negative, and that makes 4 combinations in total. Well, now that we've got x, y, and z, and each of those can be positive or negative, that gives us 8 combinations. And first octant is where x, y, and z are all positive. And we'll be taking a look at the origin from that view. So let's practice and see how you would try to actually sketch that on a 2-dimensional page. First of all, we tend to orient our x-axis kind of towards the bottom left corner of our page. And so there's our x-axis. And it's usually a good idea to leave lots of room above that x-axis, and maybe also to just make sure you draw this quite large so you have lots of room to indicate all the little details in our 3 dimensions. Now, we need our y-axis to be perpendicular to that, and we tend to like having our z-axis pointing up. There's only one way we can get the y-axis to point so that the axes obey the right-hand rule. We're going to need our y-axis to point to the right. And there's our y-axis right there. Now, those are perpendicular, but you would have to imagine that based on the perspective of our first octant. With the first octant, that means Z is going to be pointing straight upward now. Like I say, this is where you probably want to leave lots of vertical space above your x-axis up here so that you can draw the top of that z-axis and not run into anything else on your page above that. Okay, now that we've got that first octant view idea, let's see how we can plot a particular point. Let's take, for example, the coordinates 3, 5, 4. Okay, well, first of all, let's start off with x equal to 3. We're going to count 3 units in the positive direction along the x-axis. Now, if we want to, we could even take a look at what that point right there would be. We've only traveled in the x direction, and we haven't traveled at all in the y or z directions. So this point actually has the coordinates 3, 0, 0. We're going to do the same thing now with the y-axis and travel 5 units in the direction of positive y. And here is 5 units in the direction of positive y. But if we want to put a point there, that point would have the coordinate 0 for x, since we haven't traveled in the x direction, 5 for y, since it's 5 units in the direction of y, and 0 in the direction of z. Now, we could start off by at least finding a point that has these two different values, x equals 3 and y equals 5, but maybe with just z equals 0 for now. It may help to have a little ruler here and just put this parallel to the y-axis for a moment. And we're going to take a look at where x equals 3, and we'll travel from the point 3, 0, 0 in the direction of the positive y-axis. And now we're going to take our ruler and put that parallel to the x-axis and take a look at the point 0, 5, 0, travel in the direction of the positive x-axis, and see where these two dotted lines meet. Where those 2 points meet is a point where x is equal to 3, y is equal to 5, but we still haven't traveled in the direction of z, so this would be 0 for z. Now it's time to travel 4 units in the positive z direction. So there is z equal to 4 on the z-axis. If we wish to put a point there, then the coordinates of that point would be 0 for x, 0 for y, and 4 for z. Okay, now let's see if we can find a point with x equals 3, y equals 5, and with z equal to 4. That would be the point P that we are trying to look for. Well, at this point in time, we're going to take our ruler and we're going to put that parallel to the z-axis. If you want to, you could even measure 4 units, but I also have grid paper here, so I'm going to be traveling exactly 4 units straight up. I'll do that from here, and that gives me a point that is at the coordinate 3, 5, 4. Now, if you also wanted to kind of illustrate that this is in fact where z is equal to 4, you could indicate a line from the point 0, 0, 4, and you can see that that would be a line that is actually going to be parallel to the xy plane, the plane formed down here by our blue and red axes. So that dotted line from 0, 0, 4 to 3, 5, 4, since it is a constant z this entire time, is exactly 4 units above the xy plane, where z is always equal to 0. And that's how we might try to visualize these points on a 2-dimensional plane. If we're just stuck with paper as our only means of being able to do mathematics, then this is a common view for being able to visualize those points. It can be a little bit easier with a computer, and we might be able to animate and rotate in real time, and you get a better sense of that 3-dimensional space. Now that we know how to sort of visualize 3 dimensions and 3-dimensional points, we can kind of start building some of the real basics of geometry. Let's start off with distance. And not just distance in R3, but let's take a look at distance in n-dimensional space in general. And we can even start off with distance on the real number line in 1 dimension. Now, here is that real number line, or our 1-dimensional space. And I've got the point where x is equal to a and the point where x is equal to b. Now, what is the distance here? That measures a positive value, whereas displacement from one position to another could be negative. Distance needs to be positive. So we have to be a little careful here. We're going to take a look at the difference between x equals a and x equals b. That difference is literally b minus a. And we will take that and make sure that it is positive by looking at its absolute value. And let's call that distance d. That's our distance formula in one dimension. Now let's see if you remember how to find distance in two-dimensional space. Now in two-dimensional space, we're going to have 2 points that are ordered pairs. This could be point A, and we'll use capital A for this point and capital B for this point. Now, each of those points is an ordered pair, so it has to have 2 components. And let's say that point A has the coordinate A1 for x and A2 for y. And the point B, let's also have kind of a similar naming scheme. X is equal to B1 and y is equal to B2. Okay, well, as you probably guessed by using this right angle triangle I've drawn here, we need to use Pythagorean's theorem. We need to take the horizontal distance squared and the vertical distance squared, add those together, and square root. Now the good news here is that b1 minus a1, whether it's positive or negative, doesn't really matter because we're going to be squaring it anyways. Similarly, for our vertical distance, we can just choose b2 minus a2. And whether or not that's positive or negative, that's okay because it'll be squared when we look for the distance between the 2 points overall. Adding the sum of those squares and square rooting gives us a positive value again for the distance between point capital A and point capital B. Now, let's expand upon that and take a look at three-dimensional space. Now here I haven't drawn the x, y, and z axes, but you can imagine that our blue lines here run parallel to the x-axis, our red lines run parallel to the y-axis, and our green line runs parallel to the z-axis here in first octant view. Now for convenience, let's label these 2 points in the same kind of naming scheme as we just used in the previous example. That gives us the order triples A1, A2, A3 for point A, and B1, B2, B3 for point B. Now, try to imagine what these various different line segments have for their lengths. The length along our x-axis will just be the difference between the 2 x-coordinates, B1 minus A1 or A1 minus B1. It's not going to matter too much overall when we take a look at the distance formula when we are going to be squaring these lengths in order to get the length of hypotenuses. The distance along the y-axis is the difference between A2 and B2, so let's just assume B2 minus A2. And the distance along the z-axis, vertically maybe out of the page normally, would be the difference B3 minus A3. Okay, now I've also drawn a purple diagonal line here, which is the hypotenuse of that red-blue triangle. Now as it turns out, the length of that purple dashed line is precisely the distance formula in R2. B1 minus A1 all squared plus B2 minus A2 all squared, and then sum those and square root the result. Now that is going to form the basis of another right angle triangle that gets us the actual distance that we need, and using the green distance B3 minus A3. So for that triangle, we need to square our purple side. That cancels the square root, and we have to add the length of that green side squared, B3 minus A3 all squared, and then we have to square root the result again, and that gets us our distance. Now you can probably see this great looking pattern between R2 and R3. They're almost the same. Going back to that distance formula in our first dimension, d equals the absolute value of b minus a, it doesn't seem to quite match that pattern. But if you think about it, the absolute value is exactly the same thing as taking a value squared and square rooting. So we could write that distance formula in one dimension as b minus a squared and then square rooted. And now you can see this perfect pattern just develop in one dimension at a time. So if we wanted to write the formula for the distance in Rn, we need to come up with 2 points. We could have point A be A1, A2, A3, and all the way on to AN, and point B being the point B1, B2, B3, and so on until we reach Bn. And to get our distance, we're going to be summing the squares of the differences in each dimension Using sigma notation, that could be written as bi minus ai squared from I equals 1 to n and summing those. And then we have to take that result and square root it. And it may be a little more useful to write a power of 1/2. Now this particular formula that we use for distance is kind of the basis of all of our geometry. Taking those differences in each of the different dimensions, squaring them and square rooting them gives us distance, and we use that for everything. Like, just imagine if we had chosen instead to maybe cube those differences and cube root them. What would geometry look like at that point in time? And that is a whole other branch of mathematics that you can get into. So you can get some pretty wild non-Euclidean geometry, but we'll stick to this for now. With this distance formula, let's do a couple examples and find distances between points in n-dimensional space. Now, switching things up here a little bit, and we're going to find the distance between points P and Q rather than A and B. You know, P for point and Q because, well, it's the next letter in the alphabet. We often use P and Q for points. Now, I've got one example here in 3-dimensional space and one example in 4-dimensional space, but the formula in general isn't really any different. So let's start off with this 3-dimensional example. Now, it doesn't really matter whether we are subtracting our coordinate from Q minus a coordinate from P or vice versa, but it is good to be consistent. So let's start off with 3 minus -1 and be consistent with -1 minus 2 and -7 minus 5. Square all of those and then make sure we square root the result, and we'll call the distance d. Now, it's fairly straightforward math from this point on. The important part here is that those negative signs aren't going to matter when we square them. 4 squared plus 3 squared plus 12 squared. That gets us the square root of 169, which is equal to 13. Now, I use this example specifically because it's very rare to find that the distance between two integer points like this is an integer. You may remember from 2-dimensional space, a very common triangle is our 3, 4, 5 triangle. 3, 4, and then 5 on the hypotenuse. Well, in 3 dimensions, I'm actually using that triangle here again. The 3 and the 4 give a hypotenuse of 5. But then I've also added a z dimension of 12 units, and 5, 12, and 13 also share this nice relationship. 5 squared plus 12 squared equals 13 squared. So we have this really interesting 3-dimensional sort of triangular problem of a 3, 4, 12 that gets us a distance of 13 overall. All right. Can't guarantee anything here about 4 dimensions. Let's just try this formula out in 4-dimensional space. As you can see, there's nothing really any different about this. Although as the formula becomes longer and longer, it becomes more and more advantageous to perhaps just put the entire summation in brackets and use exponent notation instead. We'll do the brackets first and then sum up these squares. Like I say, no guarantees that this is going to be a nice number, but we have the square root of 55. If you think about it, distance is some kind of function that can take as many dimensions as we like, apply some sort of computational formula to it, and it produces just a single real number. So this is kind of a glimpse of what a multivariable function looks like, but we'll be taking a look at those more specifically in a future video. Okay, those are some real basics there. What if we were to take some of this idea of geometry and points in n-dimensional space and think about what that would mean for graphs? And we'll be taking a look at graphs a lot more when we start talking about functions. For graphs in n-dimensional space, just like graphs in 2-dimensional space, it's really just a set of points. In this case, not just ordered pairs, but n tuples that satisfy the given relationship. And that relationship could be a function, and we'll be taking a look at multivariable functions in a future video, or it could be in the sense of just some kind of equation that relates these different values for each point. Well, we can just scratch the surface of graphs for now by thinking about what graphs look like in 1, 2, and 3-dimensional space. In 1 dimension, we don't really have a lot to work with. We simply just have our x-axis. And if we were to say, as an example, x equals 2, that gives us a single point. And that would just be here labeled as 2. Let's take that same equation, x equals 2, and think about what that gives us in 2-dimensional space. In two-dimensional space, well, we have our x and y axis, and here I've ticked off the value where x is equal to 2. But now that we have a y-axis, the set of points that satisfies x equals 2 is not just limited to a single point anymore. We have one point that is at the coordinate 2, 0, but 2, 1, 2, 2, or 2, the negative square root of 13 would also be just as good for satisfying this relationship. So that actually gives us the equation of a vertical line. All of the points above or below the point 2, 0 also satisfy that given relationship where x is equal to 2. So we've gone from x equals 2 representing a point to x equal 2 representing a line now. Okay, well, let's go one further now and take a look at R3. In R3, we have our x and a y, but also a z-axis, and here I've labeled where x is equal to 2. And of course, if we just have x equals 2, then the coordinate 2, 0, 0 satisfies this given relationship x equals 2. But y and z can be anything. That means we can move in the direction of the y-axis, positive or negative, but we can also move in the direction of the z-axis, positive or negative. Since we have two dimensions here to move in, we can think about two-dimensional space, which is our usual sheet of paper that we're working on. It's an entire plane of existence. Well, this would mean that the points that satisfy x equals 2 is actually a plane. And here is that basic idea of that plane. You can see that we can be traveling up or down the z-axis, out and in from the y-axis, and we have this whole shaded region. Now, this continues on infinitely. I can only really sketch just an idea of what that part of a plane would look like close to our actual x-axis, but it goes on forever. So keep that in mind. X equals 2 is kind of hard to understand unless we know how many dimensions we're talking about. X equals 2 is the equation for a point, a line, or a plane. And in fact, it can even get extended into 4 or more dimensions. We just need to know kind of what the context is. R3 is going to be a very common context since it's three-dimensional space. It's what we exist in. It's what we can kind of visualize. But we just need to know how many variables there are, how many different axes we're working with to get an idea of what the graph of that equation looks like. What if we were to maybe switch this instead of x equals 2 to something involving another variable? For instance, what if we had z equal to 4, for instance? Well, since it's typically implied that our first axis is x and our second axis is y, and we don't get a z-axis until R3, this probably only makes sense in the context of 3 or more dimensions. So let's start off with maybe our first octant view. And from that first octant view, we'll need to count 4 units up the z-axis. And from there, we can travel in the direction of either x or y. And doing that will result in the graph of a plane again. This plane is parallel to the plane formed by the x and y axis, which we just call the xy plane. It just happens to be 4 units further above that. Now, what if we were to take a look at an equation involving 2 or more variables? Let's start off with a very basic example like y equals x. Now, y equals x, you should already be familiar with in two-dimensional space. In two-dimensional space, that's just the graph of a diagonal line passing through the origin. But now we're going to be taking a look at three-dimensional space, and this is going to now form a graph consisting of all of the ordered triples, x, y, and z, where x and y are the same value, and z can be anything we like. Let's see what that looks like in first octant view. We can imagine that all of the points on the line y equals x in two-dimensional space are just points in three-dimensional space where z equals 0. So that line might look something like this. It would just be a set of points that always have z equal to 0, and will include points like 1, 1, 0, 2, 2, 0, and so on. But now z is free. We only have the z direction as being the one direction we can travel, but we can travel above or below each of these points. If that's the case, then we also, again, form a plane. It just happens to be a plane that's going through the z-axis at a diagonal. It can be a little bit tough to try to sketch this, but you can try your best here with some straight lines. And get this kind of an idea of a plane that is perpendicular to the xy plane and has this nice 45-degree sort of angle with respect to the positive x-axis rotating around the z-axis. It's a little bit trickier to try to visualize. Now, we'll be taking a look at graphs a lot more extensively when we start taking a look at functions in 3 dimensions, but there's one last common shape that we often see in geometry that I'd like to make sure you're at least familiar with now, and that's the concept of circles and spheres in n-dimensional space. In this picture, I've drawn a circle of radius r centered at the point a1, a2. Now, the first question I'd like you to ask yourself is, how do you even define a circle? What the heck is a circle if you had to explain it to somebody who had never, ever seen a circle before? Just being able to say it's round isn't quite sufficient because lots of other shapes are round. Really, the only way we can define a circle is as a set of points that are a fixed distance r away from a point that is called the center. And so our center point is a1, a2, and that fixed distance is r. And we have a formula for distance. If we let x and y be an arbitrary point anywhere on the circle, then the distance, x minus a1 squared plus y minus a2 all square rooted, must always be equal to r. Well, we get the equation of that circle by squaring both sides. That is our equation of a circle in 2-dimensional space centered at the point a1, a2. And that's just the set of points on the outside of the circle. If we wanted to include all of the points on the inside of that circle as well, instead of calling it a circle, we would call that a disk. The only difference there is that it would include all of the points with a distance less than or equal to r. And since distance is always going to be positive, we could write the equation of the disk as x minus a1 squared plus y minus a2 squared less than or equal to r squared. We can extend this concept to a sphere. A sphere is nothing more than the set of points that are equidistant from a center point. That distance we could also call r. Well, a little off-camera work here. There's what that sphere might try to look like in first octant view. And we're just going to be using our distance formula again to come up with the equation of a sphere. To do that, we're going to have a point on the surface of the sphere. We'll call that an arbitrary point with coordinates x, y, and z. And we'll let that distance be r. And with our center point, a1, a2, a3, there's our distance formula with the distance always equal to r, and we'll square both sides of that formula to come up with the equation of a sphere. And there's the equation of our sphere, x minus a1 squared plus y minus a2 squared plus z minus a3 squared all equal r squared. Now, if we wanted to include all of the points on the interior of that sphere, we might call that a ball instead of a sphere, and we only have to change that equal sign to a less than or equal to sign. Now, we can take this concept of a sphere or a ball or a circle and disk, and we can extend that either backwards to 1 dimension or forward to as many dimensions as we like. Let's take a look and see what this idea of a sphere is in just 1 dimension. In 1 dimension, if we just have our distance, x minus a squared square rooted equal to r, this is the same thing as the absolute value of x minus a equal to r. And that means that x is exactly r units away from x equals a, either to the left or to the right. So this idea of a circle or a sphere in 1 dimension is really just 2 points equidistant from x equals a. And instead of having a ball or a disk, if we were just to replace this with a less than or equal to symbol, then on the real number line, this would include all of the points from a minus r to a plus r. And we would end up with an interval. We could use square brackets to include those points or shaded dots. And there is our interval. So this idea extends backwards to 1 dimension as well. Now, of course, the idea of a sphere or a ball can be extended higher into higher dimensions as well. Don't even try to draw it. It doesn't make any sense necessarily to visualize it, but we can still conceptualize it as being points in n-dimensional space that are equidistant from some center point, or if you want to include the interior points, that's just slightly different, just be a less than or equal to distance instead. We have the idea of an n sphere or an n ball, but it's pretty much the same. If you want to try to conceptualize what it would be like to get to that higher dimension, kind of picture this. In one dimension, you can imagine that you're just a little ant here, and you're sitting at x equals a. And you have these two walls in front and behind you. And you want to travel in a direction that doesn't get you any closer to one of those two walls. That's okay, it's possible. You can travel up or down. And you just invented that second dimension. Well, now you have to go and picture yourself in two dimensions and imagine yourself in the center of this ring here. And at that very center point of a circle, imagine you had to travel in a particular direction so that you didn't get closer to any edge of this ring around you. Well, you just have to get a ladder and travel perfectly straight up or down into that third dimension. To get an understanding of what a fourth dimension would be like, you have to picture yourself inside of a closed sphere. You're completely walled in by this sphere now. Now, if you were able to try to visualize this fourth dimension, that would just be your easy exit out of this sphere. It would be the direction in which you would travel so that you don't get any closer to any point on this sphere. So you can try to imagine that a little bit. Now, we'll end it there. That's a lot of conceptual ideas of n-dimensional space, starting with one dimension and just from kind of reviewing some of those basic geometry properties and inequality properties of one dimension, traveling forward into two-dimensional, and that's pretty common, pretty used to that. But taking those concepts and seeing how they can still be kind of familiar in three-dimensional space and how to look at that first octave view, plot points, see our coordinates, get the idea of what planes would look like, and then beyond that. Not being able to visualize them anymore, but still being able to kind of conceptualize how geometry continues on into as many dimensions as we like. We'll have lots of fun with this later on. We're going to be taking a look next a little bit more about some of the sort of directions and components of what we can do with coordinates in three-dimensional space. So stay tuned. Thanks for watching, and I'll see you in the next video.